Smooth clap. Okay. Hi, everybody. It's my great pleasure to introduce Alex Damian today for our speaker. He's currently a Kepner Research Fellow at the Kepner Institute at Harvard University. He received his PhD in Applied and Computational Math at Princeton University under the supervision of Jason Lee, and he did his bachelor's in mathematics at Duke University under Cynthia Rudin and Hao-Tiang Wu. So we're very excited to hear about Alex's work. Alex, take it away.
Yeah, thank you so much for the introduction. I really appreciate it. Let me make sure that screen sharing works. All right, all good. Can everyone see my screen? All right,
Yep.
amazing. So, yeah, I'm going to be broadly talking about some of my work on trying to understand optimization in deep learning. This has a bunch of different aspects. Some of them are mathematically rigorous, some of them are not fully mathematically rigorous, but seem very suggestive of a roadmap towards a theory. And so I'll talk about all of that. So just to kind of set the stage, optimization in deep learning is in a bit of a strange place right now and has been for quite a long time. So I think the first and probably most important paper in optimization for deep learning was the original Atom paper from 2015. So this is definitely the most important optimizer used in deep learning, just period, since 2015. Basically, every large language model is trained with it, maybe with a few exceptions in the past few months. Um, and kind of the surprising thing about Atom is that it really wasn't like a theoretical algorithm. Like there was kind of some theoretical motivation, but even that proof turned out to be broken. And really the reason that people use Atom is just it has really, really strong empirical results. So it's both that it's a very strong optimizer and it seems like much easier to tune than equivalent methods. And it's not so sensitive to the hyperparameters. So it's a really good default choice. Um, but even when you use Atom, it's kind of a tricky thing to get right. So this was a paper from Google trying to train a large language model back before all of the like when the labs were still publishing research and before they all closed down to the outside world. So this is from the Palm paper. And here they talked about this phenomenon that's actually still true to this day, which is when you train these large models, you get these crazy loss spikes during training. And so here they said they observed these spikes roughly 20 times during training. And these spikes were so bad that they just completely destabilized training and you could not recover from them. And so then they had a very principled approach to this. They had no idea what was going on. And so they would restart from a previous checkpoint that they saved. They would reshuffle the data, and then they would just train again and hope that you didn't spike this time. And, it worked for a little bit, and then it spiked again. They kind of had to play this trick again. They did it like 20 times. And at the end, they ended up with some sort of trained model. So, sounds kind of crazy, but this is just what you have to do. More recently, there was this paper, like the DeepSeek Techno Report from 2024, which also gave like some glimpse into the training recipe. And here, I just wanted to highlight that they have the craziest learning rate schedule I've personally ever seen. So when you're choosing your learning rate, they first have to linearly increase it, then keep it constant, then decay it, then keep it constant again, and then switch it to another constant. So, this is just what's required to get things to work. And at the same time, they're also doing a ramp with the batch size. And then finally, more recently from this year, there's another technical report from DeepSeek where they just pointed out that these same instabilities that were pointed out in the 2022 Palm paper haven't really disappeared. And they still have no idea why they're happening. So this is kind of this backdrop for optimization in deep learning where we really understand very little, and there's a lot of tricks that are necessary to make things work. So the question that I really want to ask in this talk is how do the optimizer and its hyperparameters affect the optimization process? So differences between SGD and Atom, what do the learning rates do? What does the other Atom hyperparameters do, etc. And what I'm going to argue in this talk is that the challenge, the main difficulty in optimization theory and in trying to understand optimization in deep learning is that classical optimization theory really isn't capturing the optimization dynamics of real neural networks when they're being trained by these optimizers. So, you always make idealized assumptions, but at the end of the day, people do train these models using these optimizers. And so you really want to understand them in the exact settings in which they're being used. And the claim is just in these settings, a lot of the rules break, and understanding it is a challenge. So this talk is going to be broken into two parts. In the first part, I'm going to focus on the simplest possible optimizer, which is just gradient descent. And I'm going to show how this gives rise to this concept known as the edge of stability. And then in the second half of the talk, I'm going to show how this extends to adaptive optimizers like Atom. So I kind of gave a disclaimer before, but just a bigger disclaimer that a good chunk of this talk is not going to be rigorous. I'll try and do a good job of highlighting which parts are rigorous and which parts are heuristic. But the main point of this talk is that it's some sort of mathematical theory that's very predictive. So we're going to get some sort of predictions for optimization in deep learning, and we're going to simulate these predictions on real neural networks and real data sets and show that we're really capturing what's happening. Um, so let's start with gradient descent, the absolute simplest possible optimizer. So here, W is the parameters of our neural network, and at every step, we're just going to take full batch gradient steps of size eta. So eta is the step size, and we're going to literally, there's no stochasticity in this process here. We're just going to compute this gradient over our entire data set. So I think basically all of the intuition for gradient descent you can get from the one-dimensional quadratic setting. So I'm just going to first focus on this for a second. So you look at this one-dimensional quadratic, 1/2 SW squared. The gradient of this is just S times W. So then gradient descent follows this multiplicative update rule where at every step you multiply by 1 minus eta times S, where S is the sharpness of the quadratic, how tall it is. And so this immediately puts you into two different regimes. If this number 1 minus eta S has an absolute value less than 1, then you're multiplying by a number with absolute value less than 1 at every step, which means you'll eventually converge to 0. And you might converge to 0 nicely while remaining on one side of the quadratic, or you might bounce around from side to side, but the point is you're still stable. On the other hand, if this number has absolute value bigger than 1, then you're going to bounce from side to side and blow up to infinity. So we call this unstable. And so if you want to optimize this one-dimensional quadratic, you really want to set your learning rate so that you're in this regime on the left. So in terms of your learning rate, that says that you should set it less than 2 over S, whatever S is. And this is really nice because it turns out that this is necessary and sufficient in a lot of generality in classical theory when your objective is not a quadratic, but just some arbitrary smooth function. So the classical theory basically says that gradient descent will converge whenever the sharpness, which is defined as the largest eigenvalue of the Hessian, is less than 2 over eta. So this is standing in for this scalar quantity S in the one-dimensional quadratic. So it's basically saying that gradient descent in general will converge whenever it would converge on this one-dimensional quadratic, where this S is replaced with the largest eigenvalue of the Hessian. So this is great because, we have this essentially if and only if condition. We know that if this is true, then you converge, and we know if this is not true, you'll diverge even on this one-dimensional quadratic. So, this seems like a pretty complete theory. So what is this not capturing? So to show what it's not capturing, I'm going to show a loss landscape visualization from a real neural network. So this is a vision transformer, and it's trained on CIFAR10. So I'm looking at the loss landscape of this vision transformer, and explicitly what I'm plotting is a projection of the weights. So on the x direction, I'm plotting this projection along the top Hessian eigenvector. So this is the direction in which you would blow up if you were ever unstable. And in this other direction, I'm plotting the progress direction. So the direction in which the loss is actually going to be going down. So, and at a given point, like xy point in space, I'm plotting the actual value of the loss at that point. So I'm just going to zoom in and start training. So we're starting at step 100, and then we're just going to continue training. And for a while, this kind of looks like exactly what you'd expect gradient descent to do. You're kind of following down this valley. The gradient is pointing you towards lower loss, and it's just behaving like this classical picture of gradient descent, like a ball rolling down a valley. And then in the back, we kind of see this unstable region that I've colored in red. So I'm going to color a point in red if its Hessian has an operator norm greater than 2 over eta, which means that gradient descent would be unstable on that quadratic. And we can see it's like kind of in the background, and it turns out we're going to continue approaching it. So this phenomenon has a name. It's called progressive sharpening. And essentially, it's the claim that as you continue to train, the Hessian will continue to grow until you reach this red region. You're always approaching this red region over time. So, this seems bad because now we know that locally we have to blow up. Like a Taylor expansion says that locally this is a quadratic function. And we've already seen that on quadratic functions, if the sharpness is above 2 over eta, you're supposed to blow up exponentially. And so it's kind of not obvious what's supposed to happen next because, we're in this regime where we're now going to blow up exponentially. Maybe training just diverges. Maybe we get one of these loss spikes we'll never recover from. It's really not that obvious. But it turns out if you continue training, something kind of magical happens. It looks like this. So you enter this red region and you do blow up a little bit, but then you're immediately forced back into the blue region, into the stability region. And so you're never actually blowing up to infinity. So this was given a name in this paper by a co-author of mine, Jeremy Cohen. So he pointed out in this paper that he called this the edge of stability because you're in between this red region, the unstable region, and the blue region, which is the stable region. And you're kind of bouncing between them forever. And so he pointed out that this is completely inconsistent with a bunch of things in classical optimization theory. So if your convergence analysis relies on some sort of smoothness of the loss landscape, which is some sort of global upper bound on the Hessian, this empirically doesn't hold because you always enter this red region. If your analysis only uses quadratic Taylor expansions, again, it just cannot hold because on a quadratic, you'd blow up to infinity, but here you're clearly not blowing up to infinity. And it also invalidates heuristics for step size selection. So this is kind of a serious problem. And even on gradient descent, we had no idea what was happening. So then we kind of solved this mystery in this paper called Self-stabilization from 2022, in which we described at least this dynamical system on the left that we're seeing. So we managed to write down equations for the dynamical system and analyze them. This part is actually rigorous. And we managed to show that the edge of stability is essentially just repeated cycles in which you first enter this unstable region, because you're always going to be drawn towards it. And then you begin to blow up exponentially, which is exactly what a quadratic Taylor expansion would predict. But this doesn't last forever. The key is once you begin to oscillate enough, it's immediately pushed back into the stable region. And there's a good reason for this that I'll show in a few slides that comes from a Taylor expansion. You can show it's just a generic property of any loss landscape, not a transformer, not the CFAR10, any loss function you can write down, that if you begin to blow up with gradient descent, the effect of this blow up is to immediately shove you back into the stable region. This is not obvious at all. And then once you're in the stable region, the oscillations dampen. And then this whole thing loops. So it's really this loop of like entering the unstable region, blowing up. Something, once you blow up, is pushing you back towards the stable region. And we'll describe what that something is in a few slides. And then the oscillations dampen and you re-enter this unstable region. So this is the dynamical system. And it turns out that analyzing this is not so complicated. You just can't use a quadratic. You just have to go to a cubic Taylor expansion of the loss. So if locally you pretend that your loss is quadratic, we already showed that you blow up to infinity. But if your loss is a cubic, it turns out that you can exactly analyze these self-stabilization dynamics. So now just to step back, what is the actual picture of gradient descent that you should keep in your head? So the classical picture of gradient descent is that there's some stable region S, which I've colored in blue, the same as the 3D plot from earlier. And there's an unstable region that I've colored in red. And the classical picture is that you really hope that optimization remains in this stable region. So it really says that if you run gradient descent and you never leave the stable region, then convergence is good. And you get a picture that looks like this. And what classical optimization theory would say is if you ever hit the unstable region, then you should shrink your learning rate to grow the stable region so you never escape it. The problem is that in deep learning, the picture doesn't look like this. You're always pulled towards the boundary very aggressively early on in training. So the very first thing that happens when you train a neural network is it seeks out this boundary. And then once it finds the boundary, it's going to oscillate in and out of this boundary while making progress in the tangential direction. So what's happening here is, it's kind of hard to plot this because really there's something happening in 4 dimensions, and I can't plot 4 dimensions with the animations. But what's essentially happening is that every time you leave the stable region, you get this feedback loop that's going to push you back into the stable region. This is one direction, and in other directions, you're going to continue making progress on the loss. And so you get this type of plot where you're moving along the stable region to decrease the loss, but you're really moving around the boundary because every time you leave, you're shoved back inside. And so how can we analyze this type of system? It looks kind of complicated. And our idea in this follow-up paper, Central Flows, was that we don't have to analyze these exact dynamics. These exact dynamics are really complicated. And if you want to understand the overall trajectory of gradient descent, you really want to somehow average out these oscillations. And so the real idealized trajectory looks something like this. This black dashed line is what we're going to call a central flow. It's essentially modeling the exact same trajectory as gradient descent, but we average out the oscillations. So it'll have the same loss, it'll have the same accuracy, it'll have the same trajectory, just without these oscillations built in. So this is essentially what we sought out to do in this paper, Understanding Optimization in Deep Learning with Central Flows. So the motivation was a bunch of optimizers, not just gradient descent, but also Atom and pretty much any optimizer you can think of, is oscillatory. And it's oscillatory because of some sort of edge of stability phenomenon. And the way you analyze an oscillatory optimizer is to derive a central flow, which is a differential equation that models the time-averaged optimization trajectory. So we're not going to try and model gradient descent itself. We're going to smooth gradient descent and then analyze the smooth trajectory because it's going to be a much nicer mathematical object. And then the next thing is that once we have these nice differential equations, the ultimate proof of their validity is to just simulate them. So we're going to run gradient descent, this oscillatory optimizer, and then we're going to simulate the central flow, which is just integrating a differential equation. And we're going to show that it empirically tracks the trajectory of gradient descent. And then finally, this differential equation has a closed form. You can stare at it. And then because this is no longer an oscillatory optimizer, this closed form actually has some really subtle meaning. So you can just look at this closed form and read off a bunch of behaviors of the optimizer, both for gradient descent and atom. And I'll give some concrete examples throughout the talk. So this is the game plan. So we're going to start with deriving central flows. So how do you derive a central flow? Here, WT is a cartoon for your oscillatory optimizer. So WT is the trajectory of gradient descent. So the first step is an ansatz. This is the first non-rigorous step of many. So we're going to pretend that WT is oscillating around some central flow. We don't know what it is. We're going to assume its existence. And then we're going to derive some conditions that W of t has to satisfy. And this is going to give us some equations that we can then integrate. The next assumption that we're going to make is it's not just going to oscillate around the central flow, but it's going to oscillate in a specific direction. Because we know when you're at the edge of stability, you're oscillating along the top Hessian eigenvector. This is the direction in which you're blowing up. And so if you're blowing up along the top Hessian eigenvector, we're going to make a modeling decision that we're going to pretend that WT oscillates around the central flow along this top Hessian eigenvector. And we're going to call this displacement xt. So xt is going to flip in sign at every step, and sometimes grow in magnitude and sometimes shrink in magnitude. So mathematically, we have this decomposition. So now the problem is we don't know how W bar of t evolves. So there's two steps to this. We're going to get some sort of self-consistency equations. The first is we say we don't really need to know x explicitly to figure out how W bar moves. W bar is the smooth trajectory. So in order to figure out how W bar evolves, we really only need some sort of like aggregate statistics of x. And it turns out that the right object is the variance of x. So x is going to oscillate. It's going to go through periods. It'll sometimes grow, sometimes shrink. What we want to know is if you average over a sufficiently long period of time, what is the average value of x squared? And it turns out that this is going to determine a differential equation for W bar. So this tells us if we knew how much we were oscillating, if we knew what I'm calling here sigma squared, then I know how W bar would move. The problem is I don't know sigma squared. I have no idea how much we're oscillating. We have to solve for it. And now we're going to impose an additional constraint that will let us solve for sigma squared. And the additional constraint is that you're not allowed to leave the stable region. So the central flow we said is supposed to move along the boundary of the stable region. And so it turns out that there's going to be a unique value of sigma squared that causes this trajectory to move along the boundary. So let's do step one. This is this cubic Taylor expansion that I hinted at earlier when I was showing this 3D animation. So we start with a Taylor expansion. So to first order, what we want to know is how is W bar evolving? And W bar is a time average of WT, which is just gradient descent. So we really want to know what is the average gradient along the WT trajectory. And W bar will move according to the average of all these gradients. So we'll begin Taylor expanding. What does a gradient at WT look like? So WT is just W bar plus XU. So to first order, it's just the gradient at W bar. To second order, you have this quadratic correction term. And to third order, you now have this cubic correction term. And it turns out this last term is going to be the magical term. It looks a little scary, but it turns out a lot of these terms will drop pretty quickly. So the first trick is this is really just computing the gradient at this point W sub t. So it's computing, it's computing the gradient here. But what we really want for W bar is the average gradient of WT. So it's averaging the gradient here with the gradient here along all of these different points to see on average which direction are you moving. So I'm going to denote time averages through this symbol using an expectation sign. Obviously, these are all deterministic processes. So, expectation doesn't really make sense, but really what expectation is standing in for is a local time average. So it's some sort of averaging operator. And we can just average both sides of this equation. So on the left, this gradient is the average gradient. So this is how the mean process W bar will evolve over time. And, it's equal to these three terms, but this middle one immediately drops because X is oscillating, right? So here X is positive. On the previous step, X was negative. On the step before that, X was positive. So on average, if you average over enough steps, this expectation of x term will drop. It doesn't contribute to the average direction that you move. So really all you're left with is expectation of x squared, which we've given a name. We call this sigma squared. So that's the first simplification. Already there's fewer terms. The next is that this is an equation that you may not be familiar with, but this third derivative evaluated in this eigenvector direction turns out to be a really important formula. So this is a formula you may have seen if you've ever looked into how to differentiate eigenvalues. It's kind of a strange thing. It's not something we think about very often, but the eigenvalue is just like the top eigenvalue of the Hessian is just a property of the weights. I give you a set of weights. You can compute the Hessian. You can compute the top eigenvalue. So it's just a mapping from a weights to a scalar. And it turns out that this map is differentiable. And I can actually compute the gradient of this map. There's a closed form for the gradient of this map. And it's exactly this formula here. This requires a few lines of algebra if you've never seen it before. But for now, I'm just going to take it as a given. So now you get this really magical formula, which says that what is the effect of oscillating? If I oscillate with some covariance sigma squared, what it does is it points me in the direction of the average gradient, which is the gradient plus a curvature penalty. And this curvature penalty is exactly pushing me in directions that will cut down the top eigenvalue of the Hessian. And so now we already have enough information to understand this 3D plot from before, where you were kind of bouncing in and out of the stable region. What was happening is that sigma squared was starting very small, and therefore you were just following the gradient. And this gradient was pushing you into the red region, into the unstable region. Once you were in the unstable region, sigma squared started to grow, because you're now blowing up exponentially fast, which means that this curvature penalty term starts to grow. But this curvature penalty is going to push you back into the blue region, because it's pushing you in the direction that will bring down the top eigenvalue. And the red region was exactly defined to be the region in which the top eigenvalue exceeded some threshold. So when you begin to blow up enough, this second term will overpower this first term, and it'll force you back into the blue region. And then once you're back in the blue region, sigma squared again decays, this term will again die, and you again begin following just the gradient at the bottom. So this is the dynamical system that we managed to analyze before. But now we're not going to have to analyze the dynamical system at all. It's going to be way easier than that. So the ansatz we're making now is that if we knew sigma squared, again, we don't know it, it's some complicated thing, but if we knew sigma squared, then we would say that the mean process evolves according to this differential equation. You're just going to follow this average gradient. So now the question is, what is sigma squared? Like, I can't actually integrate this equation until I know sigma squared. So how do we solve for it? The next trick is that there's a unique value of sigma squared that prevents you from blowing up. And this is now really easy to compute because now we're in continuous time land. And in continuous time, we have the chain rule, which is super powerful. So, in discrete time, if we want to compute how the sharpness changes from step to step, it's really annoying. You do some Taylor expansions, there's all these errors that we can't control, but now we're in continuous time. So if the sharpness is fixed at 2 over eta, if we're not leaving this unstable region, then we have to have that the derivative of sharpness with respect to time is exactly 0, because it's not changing. And now we can use the chain rule. So the derivative of the sharpness with respect to time is the inner product between dw dt and the gradient of the sharpness. This is just the chain rule. And now we have this ansatz for dw of dt from the top. So we can plug this in, and we get this. There's 2 terms, and these 2 terms turn out to be really interpretable. This first term is progressive sharpening. This is saying if you weren't oscillating, how fast is this gradient term, is gradient flow, trying to point you into the red region? How fast are you entering the red region? We can quantify it, and it's exactly this value. And then the second term is stabilization. It says, aha, but you're not following gradient flow. You're oscillating. You're oscillating with some variance sigma squared. So how aggressively is that pushing you back towards the stable region? And for this to be 0, it's basically saying that these 2 forces have to exactly balance each other. So the gradient is pushing you into the red region. This force is pulling you away from the red region. When do these 2 forces balance? And this is just a linear equation for sigma squared. You don't have to analyze any dynamical system. There's no complicated dynamics. You have a linear equation, you solve it, and then you plug it back into your original ODE. And now we have the central flow, because now we have a fully self-contained, self-consistent equation for W bar. The derivative of W bar with respect to time is some equation that now only depends on W bar, because sigma squared we have as a function of W bar. So now this is just an ODE, and we can integrate it. This is the central flow. So this was all this sketch where you only have one eigenvalue at the edge of stability. It turns out that many eigenvalues can be at the edge of stability, which just corresponds to having many eigenvalues of the Hessian that are bouncing around 2 over eta. So the math here gets more intense. It's not more difficult, it's just more abstract. So I'm going to quickly sketch it just for the people who might be interested. But if you don't understand the slide, that is completely fine. You won't need it for the rest of the talk. So the trick here is instead of assuming that you oscillate around the top eigenvector, just one direction, we're going to just assume that you oscillate with some covariance capital sigma that we're going to have to solve for. So we're still going to assume you oscillate around a central flow with some oscillation, and this oscillation is going to have covariance sigma. So now we need to solve for sigma. So the first thing is, again, if we knew sigma, this is the same as the little sigma squared from the previous slide. If we knew sigma, I can again tell you how W bar has to evolve. And it's just going to be according to this average gradient. And you can do some Taylor expansion to compute what the average gradient would be. But you still have to solve for capital sigma. And now we're going to impose some very basic constraints on the process that turn out to uniquely define sigma. So the first is just it has to be positive. So, if sigma is supposed to model a covariance matrix, it has to be PSD. This is non-negotiable. So we're going to assume that sigma is a PSD matrix. The second is stability. This is the same as before. We're going to assume you never leave the stable region. And now suggestively, I'm going to write this in this semi-definite domination sense that the Hessian is PSD dominated by 2 over eta times the identity matrix. But this is equivalent to the largest eigenvalue being less than 2 over eta. And finally, what we're going to assume is complementarity. So before we assumed you're only oscillating in the direction of the top eigenvector when you had one eigenvalue at the edge of stability. This is saying that you're allowed to oscillate in any of the top eigenvectors for any of the eigenvectors at the edge of stability. So if you have 3 eigenvalues at the edge of stability, you can oscillate in the span of the corresponding eigenvectors. So it turns out that this type of system has been studied before, and it's been studied in the context of contact dynamics. And people usually write it in this very strange suggestive way. And these are called differential complementarity problems. So the reason that these have been studied before is it actually makes a lot of sense when you try and imagine simulating a ball that's making contact with multiple surfaces. So let's say you have a ball that's rolling into a corner where there's multiple walls. Sigma is now going to be this normal force. And it's saying the sigma being positive is saying the wall can only push you. It can't pull you into the wall. The wall can only push you away from the wall. Stability is saying you're not allowed to literally walk through the wall. The wall is a boundary. You can't go through the wall. And then complementarity is saying that you'll only feel a normal force from the wall if you're at the boundary with that wall. If you're far away from the wall, then sigma can't be pushing you in that direction. So you're only making contact in the directions in which you actually are making contact with the wall. So, these things show up a lot in these contact dynamic problems, but it turns out that they also model the trajectory of gradient descent. So to go back, we were trying to derive this sort of central flow that would live along the boundary between the stable and unstable regions, and we derived some horrible formulas. It turns out that these formulas actually can be interpreted much more simply using this contact dynamics interpretation. So if we zoom in, it turns out that this central flow can be reinterpreted as a projected gradient flow. So what this means is at every point in time, I'm at some point W and I want to take a step on the central flow. What I do is I compute the gradient and I look at the negative gradient direction. And this negative gradient direction will probably push me outside of the stable region. So I can't just follow the negative gradient like I would with gradient flow. Instead, what I have to do is I have to take this tangent vector, the negative gradient, and project it onto the tangent space of the stable region. So I'm literally projecting out the component of the gradient that would push me outside of the stable region. And now I'm just going to follow this tangent direction. And if I just integrate this, I'll get some flow that moves along the tangent direction. And this has a bunch of nice implications. For example, you can easily prove that the loss for projected gradient flow is monotonically decreasing, even though the loss for gradient descent is not monotonically decreasing because of the oscillations. So the answer to why does gradient descent converge, even though the loss doesn't go down monotonically, and you have all of these weird spikes, is that with projected gradient flow, the loss goes down monotonically, and you're just oscillating around this monotonic trajectory. So finally, we had to do the empirical verification. So we started with some phenomenon that we wanted to understand. We did a bunch of math. It was very sketchy math. We didn't prove anything to derive these differential equations, these central flows. And so the ultimate test, given that we didn't actually prove that they're correct, is are they correct empirically? And so what I'm showing in this is we trained a bunch of different models. So some convolutional networks, some vision transformers, a ResNet, and a bunch of language models as well. And we're training these language models using gradient descent. And these are the colored lines with different learning rates. And with those same learning rates, we're then simulating this differential equation, the central flow. And we can see that it's essentially doing exactly what we wanted, which is averaging out, smoothing out the gradient descent trajectory. So it's going to match long-term training trajectories, but it's averaging out all of these local oscillations. And I don't think I have the plot in this talk, but it even agrees in weight space. So if you even look at the weight space distance between gradient descent and the central flow, it's really small, while gradient flow is a terrible approximation. So the other point I want to make, this is almost more philosophical, is that the central flow is really the true process here. We started this whole thing by saying we want to understand gradient descent. Gradient descent is so complicated. Let's try and come up with some sort of simpler process that is easier to understand. But I want to go take that a step further and say, actually, the right way to think about gradient descent is as a corruption of the central flow. And so here what I'm going to plot is evolving over time a network prediction for some sample. So there's some image. This is an image classification task, and the network has to predict whether or not this is a cat or a dog. So I'm looking at that specific logit over time, cat versus dog. And you can see that it starts pretty unsure. And then for gradient descent, its prediction is kind of oscillating wildly. While for the central flow, the prediction is very gradually moving towards cat. And this is actually really bad from a practitioner's perspective. Because imagine that you're training this model, and then at some point you want to know, does my model think this image is a cat or a dog? It turns out that this is going to depend on whether you evaluate it on an even or an odd iterate. So if I save my checkpoint at step 4,200, it'll be very confident it's a dog. It'll be like confidence 0.3, this is a dog. But then if I save it at step 4,201, it'll be equally confident it's a cat. This is kind of a disaster. Whereas along the central flow, you can see, oh, it's actually not very confident at all. It thinks it might be a cat, but it's really not sure. And so if you just look at the raw gradient descent trajectory, it's really just a corrupted version of the central flow. And if you look at the raw iterates themselves, you can draw a lot of misleading conclusions. So that's it for the gradient descent part of the talk. And now I want to spend the rest of the talk on RMS prop or ADAM, adaptive optimization, essentially. And this is because all transformers are trained with some variant of RMS prop or ADAM. And even when you use newer optimizers like muon, you still need at least a few layers to be optimized with RMS prop. So it's really just been an optimizer that's here to stay. The way RMS prop works is that you always maintain this exponential moving average of the element-wise squared gradients. So while you're training, you compute the gradients, you square them element-wise, and you put them in this buffer, which is nu. And then you use these to determine these effective step sizes per each coordinate. So the gradient is now not just multiplied by a step size that's global. Every coordinate of the gradient has its own step size. So, this is a great algorithm. You train neural nets with it and the loss just goes down really fast. But we really don't understand this optimizer. This came out over a decade ago. And some basic questions are still unanswered. So my favorite two questions are, people call this an adaptive method. So if ADAM is adaptive, then what is actually adapting to? It's really only computing gradients. It's not clear what property of the local loss landscape you're adapting to. And the second thing is, if ADAM is adaptive, if it's adapting to the local loss landscape, then what does the learning rate do? Shouldn't it just automatically tune the learning rate, then the learning rate kind of disappears? Why is there a learning rate in ADAM? And, this might look like a funny question because it seems like just from the definition of ADAM, it adapts to the gradient scale. You're just normalizing the gradients by its average norm. This is kind of the obvious answer. And I want to claim that this is really not the obvious answer. So here I'm plotting over time the coordinates of this preconditioner just for some neural network. And you can see that the gradient squared is a super oscillatory quantity. So each of these coordinates, when you look at the element-wise gradients and you square them, they oscillate like crazy. They don't have any predictable pattern to them. And then this preconditioner is trying to maintain an exponential moving average of this crazy process. And it turns out that what's going wrong in this story is that, like gradient descent, RMS prop operates at the edge of stability. And anytime you're at the edge of stability, all of the cause and effect of the process become very complicated. So here, it's not that you're adapting to the gradients. The gradients are oscillating like crazy, and the gradient norms are really large because you're oscillating at the edge of stability. So then what you're really adapting to is the edge of stability. What does that actually mean? So let's do a few lines of math to connect this to gradient descent. So the first observation is that while ADAM might look really scary, it's really just gradient descent with some evolving preconditioner. So here P is this diagonal matrix with all of these effective step sizes. And then you're just updating, instead of using these effective step sizes, you're using a preconditioned gradient. And on a quadratic, if you just look at what does preconditioned gradient descent do, you get, again, this multiplicative update rule, I minus P inverse H. And so you again have these two stability regions where now instead of stability depending on the top eigenvalue of the Hessian, it depends on the eigenvalues of this effective Hessian, where instead of looking at H, you look at P inverse H. So you're preconditioning the Hessian and you look at its eigenvalues. And you can just see from this update rule that you're going to be locally stable when this thing has eigenvalues at most 2. That way this matrix I minus P inverse H is a contraction. So now this immediately defines some notion of edge of stability depending on this effective Hessian, and we can just train neural nets and see if you're actually at the edge of stability. So here, this is RMS prop on some ResNet trained on CFAR 10, and you can see that very early on in training, you reach the edge of stability and stay there, just like for gradient descent. And just as a reminder, anytime you're above this cutoff, it means that locally on the quadratic Taylor expansion, you're blowing up. And when you're below this cutoff, you're converging. So this is really some notion of edge of stability. So let's try and understand what are the dynamics of RMS prop at the edge of stability. I just want to give some sense of what are the forces involved and how are they correlated. So I'm going to show some sort of force diagram here where blue arrows are positive feedback, meaning increasing the thing at the tail of the arrow will increase the thing at the head of the arrow. And then a red arrow will be negative feedback, meaning that if you increase one, you decrease the other. So the first is just the fundamental quantity for edge of stability is this effective Hessian. And this effective Hessian has two things that go into it, the Hessian and the effective learning rates, which are this P inverse. And so if you increase the Hessian, the effective Hessian goes up. And if you increase the learning rates, the effective Hessian also goes up. So we have two elements of positive feedback. So this Hessian is still getting hit by progressive sharpening. So we said at the beginning of the talk that the Hessian likes to grow over time. And unless there's some other force pushing it down, the Hessian will just grow over time. So this is progressive sharpening. The other thing is that we finally have our first negative feedback, which is between the gradient and these learning rates. And this is because nu, the second moment, is an EMA of the squared gradients, and the learning rates are like 1 over these gradients, which means that if the gradients grow, the learning rates will shrink. So now we have negative feedback in the system. Finally, we know that the effect at the edge of stability is oscillation. So when this effective Hessian crosses some threshold, you'll begin to oscillate exponentially. And these oscillations now have a bunch of downstream effects. So the first downstream effect is exactly like for gradient descent, which is that when you begin to oscillate, it induces some curvature penalty, and it drives you away from this unstable region by decreasing the Hessian. So this is exactly the mechanism for gradient descent. This is the self-stabilization mechanism. But now there's a new mechanism which is kind of unique to RMS prop, which is that when you oscillate, the gradients get really big. And so you now have this positive feedback on the bottom. So when you want to read some sort of diagram like this to understand whether or not a system will blow up, the important thing is that it's a negative feedback loop. And the way you can check if it's a negative feedback loop is that on every closed cycle in this graph, you need to have an odd number of red edges, which will guarantee that if you increase something, eventually that will cycle back to cause a decrease in that same thing. So here we can look at the two cycles in this graph. If we look at the top, this is the negative feedback loop of gradient descent, which said that progressive sharpening is forcing energy into the system, but the system never blows up because as it begins to blow up and you begin to oscillate, this red arrow pushes the Hessian back down. So this is negative feedback. But now we have a new negative feedback loop that's unique to adaptive optimizers, which is that as you begin to blow up, you begin to oscillate, which blows up your gradients, which then shrinks your effective learning rates. And then this also restabilizes training. So in general, the full story is this combination of negative feedback from the top and the bottom. So, the gradient descent one was kind of annoying to analyze. In this 2022 paper, we managed to analyze it rigorously with a lot of elbow grease. The problem is that with this system, there's really no hope, I think. There's just too many moving parts, and I think actually analyzing the fine-grained dynamics is just impossible. It's too complicated of a dynamical system. But luckily, if you don't care about analyzing the fine-grained dynamics, you can use the same central flow trick, We don't need to know the exact fine-grained behavior on how you oscillate. We just need to know the variance of these oscillations on average. And it turns out that the time averaging argument from central flows generalizes super easily. So I'm not going to show all of the calculations here. They're really not that hard, and they're almost identical to the calculations for gradient descent, but just with an extra term. But I'm just going to show you the empirical results and then the final formula, which is the RMS proper atom central flow. So first, let's just validate it. So this is the same experiment as before, but now I'm also plotting the central flow in these black dashed lines. So we can see that the loss over time is predicted perfectly, and the effective Hessian eigenvalues are also predicted perfectly by the central flow. And this is because the central flow is literally capping all of these black eigenvalues at exactly 2, just like the gradient descent one. And it also holds as before for pretty much any architecture you can imagine at any learning rate. So it seems really, really general and has strong empirics. So then, what is the RMS prop central flow? I've claimed that you can derive one, and I've shown you that empirically it seems to hold. But now the most interesting thing is when you stare at it, what do you learn? What have we actually learned about this mysterious optimizer like RMS proper atom? So this is the formula for the RMS prop central flow. There's a lot of terms, and I'm going to try and break down the terms one by one because each of them has a really cute interpretation. So the first is, I'm going to ignore this term on the right. This is just preconditioned gradient flow. So dw dt is going to be p inverse times the gradient, where p is some magical diagonal preconditioner that tells you how RMS prop is setting all of its per coordinate learning rates. And it does this by essentially closing this dynamical system. In this dynamical system, it's complicated because when you increase the learning rates, this has downstream effects that will decrease them. And so you want to come up with the fixed point for this system. And this is going to be given by P star. And P star has a really nice interpretation. So what is the RMS prop preconditioner? So I'm prefacing this with crazy claim because when I first derived it, I didn't believe it. We ended up deriving that P star had to satisfy some conditions. And the conditions are a little crazy. So the claim is essentially as following. At every step, you can think of RMS prop as setting its per coordinate learning rates by following the following algorithm. So first, it's going to construct a graph G in which every vertex of this graph is a model parameter. So the number of vertices is just the number of parameters. So if I have like 100 million parameters in my neural network, I have a graph with 100 million vertices. Next, I'm going to connect each pair of nodes I and j with weight hij, where h is the Hessian. So I'm now making H the adjacency matrix of this graph. H is literally like the Hessian of your lost landscape. And now what I'm going to do once I've created this graph and I've assigned weights is I'm going to solve the max cut SDP on this graph. So in max cut, what you're trying to do is you're trying to take this graph and partition it into 2 sets so that the sum of the weights between these 2 sets is as large as possible. This turns out to be an NP-hard problem. You can't actually solve it, but you can approximate it using semi-definite programming. And the semi-definite program that gives you this approximation is exactly this semi-definite program I've written here. And it turns out that the solution to the semi-definite program, or at least the dual solution to this semi-definite program, is exactly a diagonal matrix. So if you open up the book on like semi-definite relaxations, you'll get that the dual is a diagonal matrix, and it turns out to be exactly the diagonal matrix that RMS prop uses. So then you just use a learning rate of 1 over p star for each coordinate. So the first time we derived this, we didn't believe it. It seems kind of ridiculous for there to be some connection between RMS prop and like semi-definite programming and max cut. But first, let me at least justify that this isn't such a crazy preconditioner to use. So if you stare at this SDP for a bit, there's 2 terms. And for the constraint, this is not such a crazy constraint because it's exactly the constraint for local stability. Remember that we said that you're locally stable when P inverse H is at most 2. P is the preconditioner, H is the Hessian. And we said that for preconditioned gradient descent, the condition for stability is just P inverse H at most 2, which you can just rearrange to write as H is less than 2P. So this is just the local stability constraint. It says that it's not going to pick learning rates that make you blow up. It'll just put you right on the edge of stability. This is fine. But then, because you have a diagonal preconditioner, you have many degrees of freedom. You can set these learning rates in many ways to force you to be at the edge of stability. And it's picking a very particular set of learning rates. And it turns out that you can interpret the set of learning rates as maximizing the harmonic mean of these learning rates. And the reason it's a harmonic mean is that there's 2 flips here. So you're trying to minimize the trace of the preconditioner, but the preconditioner is 1 over your learning rate. So if you want to minimize the sum of the inverse learning rates, this is the same as maximizing the harmonic mean of the learning rates. And so now we can state the RMS prop preconditioner really succinctly. It says compute the learning rates with the maximal harmonic mean that are going to be locally stable for the loss landscape as determined by the Hessian. This is just what the Max-Cut SDP is really saying. And this is not such a crazy notion of a preconditioner. You definitely want to set your learning rates as large as possible, given the Hessian. And you have to now quantify as large as possible with some metric because you have too many degrees of freedom. And for whatever reason, the metric that RMS prop picks is harmonic mean. So this is empirical proof of the claim. Because again, this is kind of a crazy claim. So what we did is we trained a bunch of neural networks and we looked at the preconditioner over time. So here nu is like this like second moment preconditioner matrix. And the dotted lines are training a real neural network and just computing checkpoints and looking at, what preconditioner is RMS prop using. And for the dashed lines, what we did is at those same checkpoints, we computed the Hessian or estimated it, and we estimated the Max-Cut SDP exactly. So we're literally solving this SDP on this slide for the Hessian. And we're just comparing the results. And you can see that after like roughly 500 steps, we're just completely dead on. So really, RMS prop is solving this SDP to get its learning rates, which again, to me is an absolutely insane claim, but the empirics back it up. So this was the first part. It said that RMS prop is just a preconditioned gradient flow with some magical preconditioner, which turns out to be given by this SDP. But there's another term here. There's this curvature penalty term. And this term is a little subtle to interpret. So remember that P star was the solution to some SDP, and the objective of this SDP was this harmonic mean of the learning rates. So what this curvature penalty is saying is move towards regions of the loss landscape where this harmonic mean is higher, where the objective of this SDP problem is higher. Which is essentially just saying go to flatter regions, because if you go to a flatter region of the loss landscape, then the Hessian is smaller, and so you can use larger learning rates without blowing up. This is a really interesting principle, and we actually gave this principle a name. We called it acceleration via regularization. Normally, when you think of adding a regularizer, you think of something like overfitting or generalization. You're like, you don't want to enter these regions of the loss landscape because it's too easy to overfit. But my claim is that even if you only cared about the training loss and you don't care about generalization at all, regularization is still a really good principle. So acceleration via regularization says that you should always use the largest step sizes you can, meaning like look at the local loss landscape and figure out how fast you can go. But you should also avoid regions of the loss landscape where you're forced to take smaller steps. So really sharp regions of the loss landscape. So if you enter in some region where the Hessian is massive, you have to take really small steps. Even if you're adapting optimally, you're adapting optimally to a really bad region. And so what this curvature penalty does is it just steers you away from these bad regions of the loss landscape. And so the visual I like to keep in my head here is you're driving a car and using the largest step sizes you can. So adaptation, this first part of ADAM that people think about, is just driving the speed limit. It's saying wherever you are on the road, there's a local speed limit. The speed limit might change. Always drive the speed limit. This is the first principle. This is fine. But this is not enough, because if you look at this diagram here, if you just continue forward and drive the speed limit, you're going to enter this dirt road, the speed limit will get smaller and smaller, your step sizes get smaller, and training slows down. Instead, what you should do is you should take this detour on the left, which is this highway with a huge speed limit of 70. This corresponds to your flatter region of the loss landscape. So the regularization is saying, yes, it's a detour, but it's a detour in which I'm allowed to take larger steps. And so long-term, it'll be worth it. So we actually put this to the test. So we have this central flow, we have this formula, and it has these two terms. And the second term is this curvature regularization term. Interestingly, this is actually the only point of the learning rate. So you see, if you cover this term up, the learning rate doesn't show up in the formula. So I asked at the beginning, if ADAM is adaptive, why do you have a learning rate? It turns out that the learning rate for ADAM is really a regularization parameter, not an optimization parameter. But this regularization controls the strength of this curvature penalty, and so controls the strength of this acceleration via regularization effect. And one really fun way to test this is to just turn this effect off. So what I'm going to show in these bottom three plots are the real RMS prop trajectory and an ablation where we just turn off this curvature regularizer, which is not a real algorithm, but at least as a flow, you can simulate it. And these are the plots that you get. So you can see RMS prop and the central flow are decreasing the loss pretty fast. And now we can actually see acceleration by regularization in action. So you train faster, like the loss for RMS prop is going down, even though we've added a regularizer. And the reason is that you're staying in flatter regions of the loss landscape. So if you remove this curvature penalty, you're very happy to enter high curvature regions of the loss landscape. And because you're in flatter regions, you can take larger steps. So when you turn this regularizer off, you can see you enter really sharp regions of the loss landscape. And as a result, you have to take really small steps. And then you can see from the training loss curve that this really hurts your loss. So this principle is really key to Atom. Why is Atom so successful is that it adapts to the loss landscape, but also it's actively avoiding bad regions of the loss landscape. So it's allowed to take larger steps over time. So just to wrap up, um, the main point of this talk is just that optimizers in deep learning are hard because they're oscillatory. Every optimizer that we've looked at is constantly oscillating along the loss landscape. And so if you want to understand it, the actual raw trajectory is not super informative. And so the way we propose to get around this is by deriving these central flows, which model the time average trajectories of oscillatory optimizers. So the ultimate test, because a lot of the math is heuristic, is that we can empirically verify that these flows predict long-term optimization trajectories in realistic settings. And then the upside is that once we have a central flow, it's just a differential equation, and you can now stare at it to easily read off an optimizer's behavior. For example, by staring at the central flow for RMS prop, we were able to read off this max cut connection. So, at a more meta level, there's just this surprising fact that when we think of these optimizers like gradient descent or Atom, they're really only computing gradients. They're only given first order information. But my claim is that they're actually implicitly implementing second order optimization strategies. So gradient descent is implicitly implementing this semi-definite constraint that the Hessian can never exceed some value. Atom is implicitly solving some crazy STP in terms of the Hessian to set its learning rates. Like these are really second order methods. But when you compute them, you're only computing first order gradients. This is really magical, and I think this is severely underexplored. And it might actually be the answer to why second order methods aren't more popular in deep learning. It's not that second order methods don't work. It's that first order methods are just way better than we give them credit for. The next is this general principle, which I think has been underexplored in optimization, which is how do we design optimizers that not only adapt to the loss landscape, which a lot of people have worked on, but also are actively avoiding high curvature regions. So even if you only care about the training loss, there's this extra principle to keep in mind. And finally, just this clickbait that RMS prop is solving max cut to determine its learning rates. And so if you want to understand Atom, you really have to grapple with max cut. So I also just want to talk about some ongoing and future work. The most basic is in rigor. So as I mentioned, like this talk is not rigorous. This is the mathematics of machine learning. It's supposed to be a talk on the mathematics of machine learning, and a lot of the math in this talk is really not rigorous. Parts of it can be made rigorous, as I mentioned from this 2022 self-stabilization paper. But really the main challenge in making this work rigorous is what assumptions are you allowed to make? Because kind of the point and the motivation of this work is that a lot of the assumptions that people make in classical optimization theory don't apply to neural networks. And assumptions are basically the foundation of any rigorous math. And so if you want to actually argue that these central flows are correct or that this is the right way to do optimization, you need to begin with some assumptions about the loss landscapes. And it's just not clear what reasonable assumptions we're allowed to make. The next is noise. So everything I talked about here is in a larger full batch setting. So, above the critical batch size, if you're familiar with that term, it'll still apply to SGD. But the main question is just, can similar arguments be used to study SGD in the small batch setting? And we have some ongoing work in this direction, and we hope to have some results on arXiv pretty soon. And finally, just applications. So a lot of this is uncovering these new principles for designing optimizers that I think are also just underexplored. And I'm curious if some of these ideas can actually just be directly used to develop new optimizers. And finally, I think the most important future work is that everything I've talked about is both data and architecture agnostic. So when I tell you go to flatter regions of the lost landscape, I don't tell you what that means. It's like, a lost landscape is handed to you from above, and then I tell you how you traverse it. But that doesn't actually say anything about where this lost landscape came from. It came from optimizing a neural net, and I never used that in this talk. And so I think probably the most important future direction in optimization is to just understand the interplay between the architecture and the optimization loss landscape. So that's it for my talk. I just want to give a huge shout out to my co-author, Jeremy Cohen, without whom none of this work would have been possible. We also have a blog post where we walk you through a lot of the derivations in the paper. And yeah, that's pretty much it. I'm happy to take any questions.
Thank you, Alex, for that excellent talk. Very interesting. So we first have a question in the chat by Hans Johansson. He
Mhm.
asks, what does this imply for optimization through barren landscapes?
Through barren landscapes.
Yeah, Hans, if you have clarification also, feel free to unmute yourself.
Thanks. It's just an expression I've heard multiple times for when you're stagnating in the loss norm.
For when you're stagnating in the loss norm, but you're saying you're still making